So, shall I continue? I got a question before the break about what if you had several vertex buffer objects, which is basically if you set this to something different than one, then how would you create your IDs? Well, basically, this is an array of IDs. So you make as many IDs as you have array objects, and then ID 1 will be referenced to 1, ID 2 will be referenced to 2, and so on and so forth. And then you use that ID when you want to bind. And then you bind one at a time. Another thing that maybe I can just mention very briefly is if you want to know what these comments do and how they're laid out and configured, you can go to this Chronos page, basically. This one. OpenGL reference page, which shows you sort of a lot of these commands, shading languages, so on and so forth. So if you want to look that up, it's all sort of listed at this one. I can make this available, append them at the end of the slides or something. Okay, so let's see if this streaming is finally. Okay, should probably get another camera. Okay, so we finished this buffer layout business. Now we basically have generated the buffers. And I talked a little about how we can configure them. Now, given the fact that you configure them in one way or another, you have to tell OpenGL how it is configured. And that you do when you fill your buffer with data, basically. So you set up these buffers, you have bound them, and now you need to fill in the data. So how do you do that? Well, you use this function GL buffer data. And like you saw in the lab, if you hard code them, you use this principle. So you put up this float of vertices. Now here you have the XYZ coordinate, XYZ coordinate, XYZ coordinate. Let's say it's a triangle, for example. And then you use this command GL buffer data. Then you say the target. Again, we deal with GL array buffers. That's what we deal with now, not any other ones. We may get back to other buffers later, but for now we will just tell them that it's an array buffer. And then you have to set off the amount of memory you need. So that you basically put here is the size of your array, basically. So you take the size of your array and you input in the second slot here. Then on the third one, you're basically uploading the data. So you put in the array here. And then you have this last here, which says usage, GL static draw. If you're going to draw the same thing over and over and over again, you can use static draw. The array doesn't change. If you want to animate something and change it over time, you just change this to dynamic draw. But in the previous lab, it was basically set to static, but because this triangle didn't really do much. Maybe except if you moved it with the arrows. Okay, now it's a very important part. It's this GL vertex attribute pointers. Here's where you tell. This is where you tell OpenGL where to find the different attributes and what they are. So now you have a layout, but you have to make sure to keep track of them, and you have to keep that track. It's basically referenced back to the vertex array object, which I showed some slides back. So first and foremost is an index. So this is the layout identifier in the shader. So when you put up the vertex shader or any other one, as I will show soon, you will have to, for this particular attribute, this is the identifier in the shader that tells you that, okay, now I'm reading positions, for example. Then it is the number of, or the size of the components per vertex you write. For example, if you want to have XYZ, you have to put it equal to 3. In lab 1, we also did that, although we could have done it differently. We could have had just XY because we were just in the plane. And then we could have set 2 here, actually, and then avoided this last 0. However, when you get to the shader, you have to set all 4 numbers, but I'll get back to that. Okay, so the size there, if you want to read colors, RGB, it's again 3, for example. Yeah. And then it's the type, the data type, which is float in this case, so we say GL float. And then if you want to normalize your data to sort of have them within some sort of within some x depth range. You can set this one to true instead of false. Then you have the stride, which I talked about if you are interleaving your data into the array. And then lastly here, it's where you start to read from, basically. So if I get back to this different layouts, if I, for example, use this configuration, I have one pointer starting there, which I call index 0, and I start reading from 0 and outwards. And then I do exactly the same on this one, I just give it another ID, so let's say it's ID1 for color. In this case, I will have to set one pointer starting at 0, reading all the positions, blah, blah, blah. And then I will have to start the other attribute pointer, this number, to the length or the size of the first chunk of data, basically, to tell it where it is. So if you're using this second one, that's how you do it. If you have the third configuration, where you have this interleave sort of data, you will also have to set the stride. So first and foremost, you have to say that when I read positions, I start at slot 0 and I read 3. And then I start, and then I should skip this 3 and I should start to read over here again. If you refer to color, you have to make an offset in this pointer, which starts to read at slot number 3 onwards and then skips 3 and so on and so forth. So I'll try to give an example. Yeah. So let's say in this case you have some vertex data or coordinates and some texture data, whatever, just 2 other coordinates. And they're interleaved like this. So you have x, y, c, u, x, y, c, u, v, and so on and so forth. Now, if you want to read positions only, you basically read these 3, and then you have to skip 2 times 4 bytes. So you have to put this stride here equal to 8, because it's the number of bytes that you actually skip. You have to set here for some reason. That's how it is, basically, because the type you set here is float, and you have to skip.
Why don't you skip 8 if in the example they want to skip U and V?
No, you have 4. You have 4 bytes per.
Oh,
yeah, sorry.
Yeah.
Sorry. You have.
Yes,
I should have said that 4 bytes per float.
Okay.
Yeah, and then you have 2 floats. UV. So you skip 8 bytes of data. If you want to skip the positions, you would, for example, you would start your pointer here, so you would set this. Oops, that was the wrong way. So you would set this one to the size of positions, and then you would set the stride to 3 times 4, 12, basically. And you start to read here, and you skip 3 and read here, and so on and so forth. So this is how you basically order this together. So this part is very important. Did you get it? Do you have any questions around that? Yeah.
So you would write 8 on this example.
Yeah, on this example, yeah, if you want to skip you and me. But that's if you choose to interleave your data, of course. In the first lab, it will not be interleave, but it will be positions first and then colors at the end. So, yeah.
Why would we choose to skip?
Because when you set one attribute pointers, and you're, for example, in your vertex shader, you wanna read the positions and then you want to pass the colors on, but you want to do that in two vectors, right? So in the first case, you should just read positions, and then that's then you use the pointer that points to position, because that tells you that now you have a position attribute. The second pointer you initialize, which you set to another index, which you saw here. We set a different number here, which, for example, 0 for position and 1 for color. Then that should read only colors, right? And if you have this interleave, you have to, since this is where you start and you end that size of, basically, you have to tell it what to skip in between. Otherwise, it will just read color data as position data, for example. And then you get, I mean, you don't get an error when you do that. You just get the wrong sort of rendering, basically. So this is maybe to avoid some debugging and those sort of things. Yeah.
So it knows that it needs to read 3 floats before skipping 2 because you specified size, right?
Sorry.
How does it know that it needs to read the first 3 floats and then skip? Like
No, you see here.
yeah, like
That number, yeah. So this is where you start in your array. This is the number of you should read per vertex, for example, and then this is the number you should skip. But yeah, and then you just yeah.
So the size is in components and the stride is in bytes. Is that correct?
Yes.
They're not measured.
No. So that's a bit unfortunate, but that has to do about what you set here will depend on what you say here, right? Whereas here is just the number here is just what you have allocated. But it's a bit confusing. But ideally, this should have just been the number of slots basically to make it easier. But then again, that's not the way it is. Any other question? Yeah.
I didn't quite get the first one. The index.
Oh yeah, this one. I'll give an example now. This is the index which you refer to in the shader. So if I set this, let's say this is position data. Now I set it equal to 0. If I want to read color data, I read it with the pointer indexed 1. Right. So it's just to separate this attribute pointer is now set to read positions because I associate that with this array. If I make another array with color data, for example, I will have to use a different attribute pointer. If I get back to, I will take it just in a minute. I'll just explain because it's important that this is. So if you look at this one, you see you have one pointer here, index 0, pointing to position. And then you have another pointer pointing to color. If you have a third attribute, you have a third pointer, and so on and so forth. This is just so you keep track of what attribute you're reading at any given time. And when you run your shader, you have to tell it what is what, basically. I think that you were first.
Yeah. Can you just go back to the slide, to the last slide?
Yeah. This one? Or no, this one.
Yeah, this one.
Yeah.
So this reads an array of positions.
Yeah.
Is there? So can we like read an array of interleaved data?
Yeah.
Without reading every data. So at the same time. Not skipping stride.
Well, you mean just reading everything in once?
Yeah.
You could, but then you wouldn't really keep track of what was what. Because when you set up your shaders, you have to, for example, in the vertex shader, you're going to set positions, and then you're going to send the colors further down the pipeline to the fragment shader where you set the colors, basically. So you could do it, but it's very inconvenient. I think that I don't think I think that would be very difficult to do it. So probably you would have a lot of things showing up that you really didn't then probably. Yeah.
The index, does it tell you which vertex the attribute is? Or?
No, the index here,
Yeah.
it's only attribute. So if you want to read position, for example, then that index should refer to position. If you want to read another attribute like color, you change it. Because here you tell the number of components per vertex, for example, or color components per vertex, and so on and so forth. So it knows when it doesn't have red 3 floats, now I have 1 vertex, right? And when you draw, you will also specify the number of vertexes you draw. Like in the triangle, you set the number 3, for example. So all this has to be sort of put together. It's a bit confusing the first times you do it, but once you get into this, it's really a nice way of organizing your data, basically. Yeah.
So the index can be whatever you want.
Yeah, whatever you want.
So you can
You could call it Pluto. I mean, it doesn't really matter. I bet it's the example I show now. I'll use 0 and 1 just to make it a bit simple. But you'll also have. I can actually show it at once. This command here, where attribute x you can get from this GL get attribute location from whatever shader program you have, and whatever attribute x over here you have. And this attribute you can use in your vertex vector array to refer to it. Then it's set up for you, and you don't really have to remember these indices and numbers. If you have very few arrays, you can just set them up manually, but if you have many and you don't want to... I think this is the cleanest way. This is what I do in lab too. But for now, I'll just show an example just to set it manually, so you see how the flow is basically on this. Okay, so maybe I can show in the lab. First, now Carl has updated this, as I said, with shaders. So he put up a vertex shader here. Don't mind the code yet. I will explain that later. Basically, you input the code as a string, and in here you set this. You set this location 0 here, which refers to the attribute pointer. So this refers to this input being positions, and this one refers to this input being color. I'll get back to this once I talked about shaders, but I will just show how to set up these things in the program first. Check if I have the streaming up and going. Yeah. Okay. So as you saw in the first lab, you had the triangle. So you put up these numbers here, which refers to vertexes. So we have 3 vertices and 3 numbers per vertex, so 9 components in total. Now I just made another array of integers or floats, which refers to colors for each node. So for example, the first line here is RGB for the lower left vertex. Then I have RGB for the lower right vertex, and then I have RGB for the upper vertex on the triangle, basically. And then I generate the vertex array, as I said, 1 vertex array. Still, I just use one vertex array up here with this ID, same as it was in the lab. And then I create 2 buffers. So first one buffer for the position coordinates. I bind it, and I upload the position data. This is exactly the same as it was in the lab. And I set the pointer. Now I call this positions attribute 0. I read 3 and 3 floats at a time, 3 floats per vertex. It's floats, and I start to read at 0, basically. So that's exactly what you had in the previous lab. And then I read in the colors. So I set up a vertex buffer for the color. So I just name it with a different identifier, vertex buffer color, and then I bind it, and I upload the data. And I create a vertex pointer. Now it's exactly the same since I used 2 buffers here. The only difference is that I now put this index equal to 1, because now I'm referring to colors, basically. Yeah.
The function GL buffer data.
Mm-hmm.
The third parameter where we send the actual array.
Yeah.
In the function signature you showed us, it was supposed to be a reference, right? But right there we're only passing a copy.
This one?
Yes, right.
Well, that's basically the array, right? Let me get back to the. I set up this array up here, right? Array of floats.
Are arrays always passed as reference?
Yes.
Yep. Okay. Good. Thanks. Because if you look at the command, let me see. Back to this. Where was it again? Yeah, so it's basically, yeah, you see it here. Void start data, basically. That's input. And then there's the reference to the array, basically, input. There's a pointer. And it's the same with the buffers, basically. It's always the ID reference to it. Okay. Yeah. So you basically set up both of them, and I have different indices. And these indices I refer back to when I put up the shaders. So I'll get back to that later. Okay. Any more questions before I move further? So what I've shown until now is how you set up your buffers, how you take in your data and you set up your buffers for your different attributes and how you keep track of them. And that's basically the hardest part of this process. It's, but once you've done it some few times, it's basically in your fingers. It's a bit a lot the first time. Now we come to the activation and drawing, or what they call the rendering loop, basically, which was in the code of lab 1, was this do loop running. So what you basically do then, you enable the attribute array you want to render. When you draw, you deactivate, update whatever you need to do, and then you swap buffers. And that you do by this GL enable vertex attribute array. Then you refer to this number you set again, which was 0 for position. If you also would like to have colors, which I do in this code I'll show you soon, you also enable 1, for example. And then you draw, and you specify the primitive, which in this previous lab was triangles, but it could also be point lines and a number of other things. I'll show you soon what you can actually put in there. And then you start from vertex 0, and you read 3 vertices in total. And you already specified that there are 3 numbers per vertex, right, in the pointer. So now you have basically added it all up. If you want to draw several more triangles, then of course you just multiply this number here with whatever number of triangles you will draw. Then you disable, and you swap windows. Yeah, this is a bit outdated. You should actually be GLFW there, but sorry for that. Now, in between here, if you want to animate some object and you want to change it during the way, you disable, you update, then you re-enable, and you draw. That you do in this loop. Okay. Yeah, so a little bit about the primitives, what you can draw in OpenGL. We've seen you can draw points and lines and triangles, basically. The rest is basically derivatives of that. So here are all the different ones. First of all, you can draw just points. It's quite straightforward. Then you can have lines in between points, or you can have this line strip, which basically connects all the points without making a loop. And then you have a line loop, which is basically, connecting all of them together in a loop, basically. Polygon is another option. It's basically also just triangles. And then you, of course, have the triangles here. And you have the triangle strip, which is very neat about this. If you draw one triangle and you want to draw a second one, you just add one node, right? And every time you add one node, you get another triangle, and you get this strip that you can make there. You also have a triangle fan, which is also drawing triangles, but all triangles have one common node. And this is nice if you want to deal with, for example, spherical geometry and those sort of things. And we have something called quads, which is basically trapezoids. They're basically triangles too, but the neat thing about them is that if you would draw this with 2 triangles, you would have to operate with 6 vertices instead of 4. Of course, you could do that, but then you would have to specify basically. So, and you can also make quad strips of them. So that's the primitives you have. The rendering loop, this do loop that's running, as I already said. You activate the input buffers, you draw, you deactivate, you swap, you modify, and then you start from top again, and this sort of goes running. So once you put up all your buffers, most of the hard work is done. Now you can start to play around with it. It's easier and more clear and explicit. Okay, so lastly I will talk about shaders. And I think I will have time to go through this now, yes. Let's see. Okay. Yeah. Okay, so we already seen, at least now in the beginning we'll deal with 2 shaders. It's a vertex shader that sets positions and a fragment shader that colors your object. Right. So as I already mentioned earlier, a shader program is basically a mini program. It's written in something called OpenGL shade language. It's very close to C, C++, has many of the same operations with the exceptions of pointers. It also has additional convenient types for vector or matrix manipulation. This vec3 is a 3-dimensional vector, vec4 is a 4-dimensional vector, and then you have map2 being a 2x2 matrix, map3 being a 3x3 matrix, and so on and so forth. And you can do matrix operations with them, so they're quite neat. We'll get back to that in the next talk or next Thursday when we talk about transforms. Now in the shaders we will have to deal with these vectors, because basically when you output something from a shader you usually end up having a vec4, because that's the coordinate system in OpenGL. But you can input vec3 vectors and then transform between them. So I'll just show examples of a vertex shader program and a fragment shader program. Basically, all shader programs has this sort of layout. So it starts off with a version, which is basically the version of OpenGL you're running. It has some inputs and some outputs and the main function. Now, these you usually define in text files, which you load into your program. So basically, you load this in as strings. Or you can write them on top or anywhere in your program as a string, basically, with using quotation marks. Now, to explain, the same with the fragment shader, same version, input, output, and main. Now, this version number, in the lab you will see in the vertex, in the shaders that you get attached with it, that you have 150. That actually refers to OpenGL version 3.2. And I think it's set that way, so it should comply with Max. But I think you will just update this number to whatever version of OpenGL you're running. So why 150 is 3.2, I don't know. It's a bit cryptical. But after 3.2, 3.3 and onwards, it's basically quite simple, because version 3.3 is 330. And 4.0, 400. If you have 4.5, you write 450 there. So you can basically just make sure that you don't put a number that's higher than the version of OpenGL you run. That you can modify. Then we have input vectors, and then you use this in command. So in vec3 position, for example, in the example I'll show you, you have a vector of positions and you have a vector of colors. And both of them I have defined as 3-dimensional vectors. Now, the shaders usually operate with these 4 vectors. So I output the 4 vector here. I could have sent a 3 here on, but then I have to deal with a 4 vector over here. But yeah. Another important thing is that in this case, I now refer to positions and I set this identifier here 0, which was the one I used in the attribute pointer, right? So in the attribute pointer, I set the index 0, and since I do it's in a read in positions here, I set it to 0 here as well. And then for colors, that was attribute pointer 1, so I set number 1 here, and that refers to input vector of colors, basically. And then I have an output vectors of colors, because colors are not going to get outputs from the vertex shading, but it's simply passed down the pipeline. So what I do with the color is I take in this 3 vector, I convert it to a 4 vector by setting in my color triplet RGB, add another 1 because I don't want my object to be transparent, and I basically output it and send it to the fragment shader where it will be executed. So that's how you do with all the data you want to pass down the pipeline. You take it in and then you send it out again. Whereas the position data I want to set here. So basically I say vec4 position, which is x, y, z, and then a 1, which is this w coordinate, which we just set equal to 1 for now. And then this vec4 is just basically given to the final clip space for rendering. I pass the color over to the fragment shader. It's where you set your colors. Of course, you can write some code in here to do some changes and animate and those sort of things. For example, if you want to change your colors, and which you're going to do in lab 2, you're going to have these dynamic colors inside triangles. You may do something in here before you output them. But in this case, I just want to output the color associated with the vertex. So I take in a color vector, I send out a color vector, and it basically puts in color equal to out color in this case, since I already converted it to a 4 vector here. Any questions? Understandable or totally not understandable, or it's a bit much in 1 hour all this if you're not accustomed to this from before. But once you sit down and do the lab, and maybe you could try to take this code that Carl has provided and try to render a colored triangle with it, as I have done now, just as a way of practicing. Because once you've done this a few times, it's basically quite obvious. But the first time, there's a lot of things you have to do to set this up right. And the problem is, if you set it up wrong, you don't get an error necessarily. You just get the wrong sort of rendering. It can be quite difficult to figure out, what went wrong, where it went wrong. Okay, so there's another list of things. When you have programmed this, put up these programs, you have to do a lot of these things. But this is basically a recipe you do every time. So you will see every time you have a shader in the program, you have to go through all these commands basically. But it's basically a fixed setup, like when you put up these windows and those sort of things in Lab 1. So when you have all these commands, I won't go into details now because it's better to just look at how it's set up in the different labs. But for example, you have to create a shader, basically creating an empty shader object. Then shader source, hence your source code to the shader object, the one I wrote on the previous slide. Then you have to compile it. And then you create a program where you sort of attach all these shader objects you have. So in the last example it was 2. Then you attach these to the program and you link them. So that when you execute, all this is sort of put into one chunk. And then in the end you delete them basically. So this you go through every time. It's a long list now, but I mean this is just a thing you repeat and repeat again in most cases. The interesting things you do inside here, basically. Okay, I will run this example of in the end before we go. Any questions to this now? There were some references given here to things you can read. These tutorials also have some information on this. But I think the best thing is to sit down and try to do some coding and figure it out how it works in that way. Because then you get a feel of things. And then you sort of start to sort this out in your head. And it's getting easier by doing it that way. Okay, so I'll just spend the last minutes trying to run this thing. So I already shown how I extended this lab. So basically, if you run the code that Carl has provided, you will get a white triangle on a dark rose background. Now I just have it on the black one because it's easier to differentiate colors from it, so I've now just done like that. So you get a white triangle on the black background. It's basically just putting this one to 0 instead of whatever was standing there. And I have exactly the same triangle. The difference I made is that instead of just saying in the fragment shader up here that I send an out vector or just once, I want to set them individually so I can change the colors. So on top of this code you will see these shaders written down, and they're basically written as strings. And you will recognize this structure, the version, inputs, output, and so on and so forth, where I set the different attributes. So in the first input vector, I read positions. In the second input vector, I read colors, and so on and so forth. I pass the colors down to the fragment shader, and I output these positions to the clip space for rendering. And then in the fragment shader, I just have one input, which is the color, so that's easy to keep track of, and then I basically output that as colors. In the code example that's online, you will see that this one is basically hard-coded to 1, so that you should always get a white triangle, but now I want to change the colors. Okay, so now I put up all these buffers, I put up all the references, I have bound them down here in the rendering loop. Basically, that's also important. Every new attribute you make, you have to enable them here for it to be drawn, otherwise it will just be skipped. Yeah. So you bind the vertex array you were talking about, and then you enable each attribute. Okay, yeah, you can also look at this code to see how you compile shaders and use that list I showed you. Okay. Yeah. Okay, so here we have the triangle, the white triangle on the black background. Now it's white because I set all these to ones. Now what if I want to color it green? What do I do?
You only set the second one to 1. The others doesn't.
Yep. Okay. So R equal to 0, G equal to 1, B equal to 0, and I do that for all vertices. And then hopefully we get a green on a black background. Now, as you asked earlier, what happens if you have different colors associated with each node? So let's say I put red down here, blue there. No, let's say red here, green there, blue on top. How would it look like? And that's essential to how OpenGL draws, because now we specified it to draw triangles, so it's basically interpolating between 3 nodes. The node down here and the node on top there. So what does it do with the colors? Anyone who has an idea?
White.
Hmm?
Is it going to be white? If we do red here, green on one.
Yeah, maybe it makes it all one.
And if we have the first vertex only red, the second only green, and the third only blue.
Okay, so we say red, green, blue. So you think it's going to get white, the whole thing?
That's how I would do it, I guess.
Yeah.
Well, I think it will be white in the middle because all the colors are like mixing together in the middle, and red on the right side, blue, and they will just like intermingle and
Mix up.
mix up.
Okay. Any other idea? Okay, so just let's set it and see. So red down in the left hand corner should be 0, and then to get green on the second I set 1 on this one, referring to the lower right vertex, and then I set 1 on the last. So let's see. There you go. So you're onto something when you say that it's interpolating, because that's exactly what it does. But you can see in between here you have the mixture, which is typically magenta, but it's a darker magenta, and it's a darker yellow, and it's a darker cyan, because in between you get half and half, right? And half magnitude. That's why you will see a gray scale or a gray tone in the middle instead of the white, basically. So that's really the essential thing of how this fragment shader works. If you associate the same color with all vertices, you get that color on your object. If you want to have different colors, you can play around with it like that.
So will essentially the color will like get radially from the vertex, right?
Yes, and then you can say that, yeah. So yeah, it will basically be. If you're in the middle, you will have 0.5 on all of them, I think, or about in the middle, right? But 0.5 green, 0.5 red there, and so on and so forth.
When we had all green the first time,
Yeah.
it was like 0.5 from each of one, so we got a continuous color, like because
It was all of them, so that they got mixed with the same, basically, the same string. But then they're all the same, so that you have the same sort of strength on all of them. You have a question? Was it someone else? Yeah. So on lab 2, you're going to play a bit around with that, but you're going to draw several triangles. I can basically show very briefly now. if I have it here. Oops. Yes. So the default you'll get is boom. No, I didn't really compile here, I think. Okay, so this is the base upset. When you just run the code that's online, you will get these different color triangles. And what you're going to do is to animate the colors so that they are dynamically changing. So something like that, for example. So if you want to start trying to do this, you can do that. Maybe if you want to do something before lab 1, you can try to make this color triangle or something. Otherwise, we will start to deal with this on next Thursday. Yeah, that's also important. On this Thursday, we will have another lecture, which is on debugging, basically. We covered that one before we start the next lab. Then next Tuesday, there will be a lab on this, and then next Thursday we'll start to talk further on transformations. Okay. Yeah, that's it for today. If you don't have any more questions, I guess we're done.